is that for reverse engineers, it's kind of more annoying, right? Well, we'll see not so much, but at least there are enough people that don't like reversing Go programs that I think anyone writing malware in Go language is going to probably go through the cracks. Anyway, what else is there here to say? Yeah, so basically, the main takeaway from this slide is that Go binaries, they're not that much more difficult, as we will see, than to reverse engineer than other programs, but they do require this sort of different approach that not everyone knows of. And so this is why I think a lot of people do not like reverse engineering Go binaries. But I mean, thanks to this tutorial, hopefully you will see that, well, it's not that big of a deal at the end of the day. So as for the malware that we will be analyzing in the course of the tutorial, after the introduction, where I show you around the Go language a little bit, we will look at Sun Shuttle. Sun Shuttle is a malware that was disclosed in the context of the SolarWinds incident. I'm pretty sure that all of you know about it. It was disclosed by CISA and Mandiant in March 2021. And Sun Shuttle specifically is the full feature backdoor that was discovered in this supply chain attack. I mean, I don't really want to go back to this SolarWinds incident in too much detail because I'm sure that most of you are familiar with it. Long story short, this is a software company that provides IT management software. It was breached, and then it was leveraged to infect very high-profile targets. So if you'd like to know more, I mean, there are so many blog posts out there. I'm pretty sure you can find more information about it. But at the end of the day, after the victims were selected through the supply chain attack, and a piece of malware was deployed to those victims, and the final piece of malware that we were deploying on victim machines is called Sun Shuttle. So this is what we will be looking at because it was written in Go language. So let's talk about how this tutorial is going to be structured. So we will do a little bit of theory, and it will be very short, right? I don't think that I don't think any of you is really interested in learning about Go language in terms of language itself. I don't think you ever want, or maybe you do, but if you do want to learn how to write proper Go programs, then probably this is not the right place. We will only figure out the most basic things that we need in order to be able to find our way through programs. We will talk about tooling a little bit, especially when it comes to IDA and the useful plugins, because there are some of them. And finally, we'll just dive into just the tutorial or the actual practical work. And we will first start with Hello World programs. Looking through those, we will kind of get our first bearings into binaries compiled with Golang. And then finally, when we have figured out the basics, then we can directly jump into an actual real-life APT malware. And then we will see how to tackle that. And we'll probably definitely won't be able to look at the whole of the Sun Shuttle malware in only 2 hours or 2 hours and a half. But I'm confident that we will see enough that you will be able to finish this on your own and then maybe look at other Go malware on your own later on as well. So anyway, let's talk a little bit about Go. The first thing that you have to know is that it generates executables that are statically built. So what does this mean? Well, it means that the whole Go runtime and all the necessary library functions ship with every program you compile. So we will see that a simple Hello World program turns out to weigh something like 2 megabytes. And in essence, this is really the reverse engineer's worst nightmare because, well, the proportion of useful code that was written by the malware author compared to the quantity of code present in binary is really very, very small, infinitesimal even. So it means that if there are, I mean, I don't know, if there's 1 kilobyte of malware code, then you will get 1.9 megabytes, 1.99 megabytes of library code that is actually completely useless and documented somewhere. So it's not great, but things used to be a lot worse. That's the silver lining. So IDA Pro, since version, I think 7.6 or something like this, introduced a lot of improvements when it comes to Go binaries, because I'm pretty sure that their customers complained about it. And so IDA has become very efficient at recognizing library functions. And that's really, really a good thing. Because in the past, you used to have to download weird projects from GitHub to maybe get this information. So maybe you would have to create type libraries out of the source code of the Go version that was used to compile a program and so on. It was really a nightmare. So now things are kind of good. So yeah, let's move on. When it comes to writing code, Go feels like a scripting language a little bit. It doesn't have semicolons. The syntax is very uncluttered, but it has very strong typing, and the compiler turns out to be very, very strict about lots of things. So if you have an unused variable somewhere, the code is not going to compile. If you have an import that isn't needed, the code won't compile. If there is a return value that you're not using, then the code won't compile either. So it's really a strict language in that sense. As far as reverse engineering is concerned, we don't care about that too much because we're not going to suffer through the compiler's whims. But it's kind of a good thing because it means that the authors of the program will be forced, or at least forced to some extent, to write proper code. And so it means that at least the code quality that we will be facing should be, it should be kind of okay, right? It means that, since the compiler forces people to write sort of clean code, it means that what we're going to have to look at is going to be, we will have to fight with the complexity of what the program is doing and so on, but we won't have to fight with the added complexity of crappy software developers, which is the case in so many malware strains that you see out there. Memory not being released with variables that are not used to anything, etc. That doesn't happen in Go language just because the compiler is not going to let you. So this is kind of a plus for us. In Go, another thing is that there is no exception mechanism. Like it just doesn't exist, or as far as I know at least. But one very important thing, one key component of the language is that the functions can return multiple return values, and that's a sort of a problem in the sense that when you look at IDA's decompiler, it tries to decompile programs to C or pseudocode that looks like C. And in C, there is just no way to represent multiple return values, right? And so the decompiler tends to be completely confused by everything that Go is doing, and so we will not be able to use it. But anyway, one thing that is important is that a very common pattern for Go functions is that they will send out a result, but they will also return a error object. And this error object represents whether this function succeeded or not. And so in many languages, you would have, I don't know, in Java or Python.NET, maybe even in C++ if you like, you would have a function that returns one value. And then if something doesn't work as expected, then it will throw an exception that will be caught, and then you can react to this. In Go, the way that it works, even for the library function, is always that the function will return both its return value, maybe multiple return values, and this error object that is hopefully null or nil in Go. One silver lining is that the standard library provided by Go is really, really extensive. It means that every time you want to be doing something a bit complex, like opening files, establishing network connection, cryptography, whatever, then you will not have to write the code on your own. You will not have to develop this to write the functions. You will just call some function from the Go standard library. And that's pretty cool because it means that most of the code that we'll be encountering from our authors is really some sort of Lego block assembly of function calls that come from the library, right? And it means that the complexity of the most complex operations will usually be offloaded to library functions. And then if we are able to recognize those library functions, which we are because the tools now are kind of efficient, then we won't have to suffer so much because we won't have to look into complex code and try to figure out that, oh yeah, this is base64, this is AES, etc. This is just going to be provided to us, and that's actually pretty cool. So the way that I will approach Go programs usually is that I will try to rewrite the original script manually. The way that I tend to do this is I try to look at all the calls to library functions. I look at all the arguments, and then based on this, usually the whole structure of the program tends to surface up. It tends to become apparent if you look at all the functions the library calls and all the arguments that are passed to it and the way that the return values are being used. And it turns out that the meaning of the program tends to be kind of apparent. So I gave you this image of Lego blocks that are assembled out of function calls to library functions. It's really what we're going to be doing there. So we know what the Lego blocks are, and we're just going to see at the big structure, the big shape that is constructed out of these blocks to figure out what the malware is doing. But we won't really be diving into each and every function. That might not be the most proper way to reverse engineer stuff, but it's actually a way that works very quickly. And this is, in many cases, what we are looking for. Anyway, when we are looking for explanations about the library code, it turns out that the Go library is pretty well done. So there is a website, it's there, golang.org/pkg. Oh, I think it changed right now. It's pkg.go.dev, but probably the old URL still works. In any case, this documentation is pretty well done. We will be using it a lot. And when we encounter a function we don't know, we can look at the documentation and we will be able to find all the information about that function, what it does, but also what the arguments are, what the return values are, and so on. And that's it. So it's pretty useful. And this is mostly what we need to know there. Another point of interest I can maybe mention is that all the strings and all the global constants that are used in the program, interestingly, can get all mashed together and stored somewhere in the binary. I'll show you that exactly in the with IDA later on. But it's kind of confusing initially, but it is the way it is, right? We best to know about it because we can't change it anyway. So I'll show you how exactly it translates, but yeah, be ready for to be a bit surprised by this. Another very important thing is how function calls are being made. Now, in Go, there are actually two ABIs. One is the older one that was used before version 1.17 and 1.18 for other architectures. And back then, the arguments, the function calls were kind of, they looked a bit like C or C-like languages in the sense that for every argument that was passed to a function, they would be pushed in the stack in reverse order. So you would see push 1, push 2, push 3, whatever, and then call to a given function. The return values are actually the same. They would come back through the stack as well. But since version 1.17, the arguments are now passed via read registers. So in the order RAX, RDX, RCX, RDI, etc. I put the link there so you can see exactly where this is. You have all the documentation on the Go website. It's very extensive. I maybe don't recommend that you look through it, but it's kind of useful to know, right? And this leads to a question, which is how do we find the Go version used to compile a program? Now, I think when you open any Go program and you look at a function call, it's going to be extremely obvious whether or not or which ABI is being used, because if you see stuff being moved to registers, then you know it's at least version 1.17. And if you see just push, 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 and then function call, then you know it's earlier than this. But still. So this is something that is sort of important to know. But I think that as time passes, then this old ABI is going to become more and more rare because, of course, now we've moved on to this register-based thingy. And this is going to be probably what they will use for, I don't know, the next 10 years or maybe forever. Interestingly, there is a blog post somewhere in Google's blog where they explain that just doing this change allowed them to get something like 50% of performance increase throughout all the programs that they tested. So just doing this simple change of passing arguments through registers instead of through the stack, which is in the memory, obviously is going to be faster, but having some metrics is pretty cool. Anyway, let's talk a little bit about the tooling. Now, in the course of this tutorial, I will be talking about IDA Pro a lot. So I apologize for this because I'm pretty sure that a lot of people out there do like Ghidra better. But I just haven't had the time to switch to Ghidra yet. Eventually I will, but I haven't been able to at the moment. So I will be talking about IDA. If you want to follow this tutorial with Ghidra, I'm pretty sure you can. But I will not be able to provide a lot of support there, right? Because I do not really know how this tool works, and so support on my side is going to be very limited. but I am pretty sure that since Ghidra has a strong community, all the plugins and all the features that I will be mentioning there have been ported one way or another to Ghidra, at least when it comes to plugins. When it comes to recognizing Go functions and Go libraries, etc., it feels to me like IDA is doing this manually. Like if you compile a program with the very last version of Go, and if you don't have the very last version of IDA, usually IDA is going to be a bit lost. So it's kind of a problem there, in my opinion. So I don't know how they are doing this with Ghidra, if they are more current or if they follow up on this, but well, maybe you can tell me. Anyway, there is, first of all, this repository, which is called Alpha Golang, was developed by my good friend, Juan Andres Guerrero Sad. He's a researcher from Sentinel-1. And yeah, he maintains this repository. I contributed one script to it. I will show you what some of these plugins do. The general idea is that some of the functions, some of the features that used to be passed like this as IDA plugins have now been integrated directly into IDA. So this repository is less crucial than it used to be, but it still contains pretty useful stuff from time to time. So I will walk you through this, the various functions or the various scripts that are contained in this repository later. And now let's talk a little bit about the samples. So if you do have IDA Pro or Ghidra, or if you have everything on your machine, you will be able to do everything locally. And this is going to be my recommended way of following this tutorial, because the other is you can use one of our online VMs. Only 30 of them are available. I think we'll be fine based on the number of people in the room. But the thing is, those VMs, they are in a data center in Amsterdam, which is kind of far from here. Usually, I tend to do trainings more in Europe. So I don't know exactly how the latency is going to work for you guys. The access to these VMs is through remote desktop or something. It's through the web browser. You can do anything from there. But there might be a little bit of delay. I don't know exactly how bearable it's going to be. So if you can use your local machine, if you have an IDA license and so on, and I suggest you use that. If this is not the case, then you're welcome to try one of those VMs. But right, the connectivity might, well, I hope it will be comfortable, but it might just not be. If you do use those VMs, the samples are going to be in a folder on the desktop. There's going to be a folder on the desktop called samples or tracks or something like this, and then you go to the very last folder, which is Go or Sun Shuttle, and then you will find everything in there. Otherwise, if you don't want to work on everything locally, you can find the archive that contains all the samples that we will be using today on this server, p.kwi.ski, which is shorthand for proxy.kwiatkowski.fr. And in there should be, if I remember to clean all my wires, there should be only one archive. And this is just a zip file containing the samples. The password is infected, as usual. And yeah, of course, it contains a sample of a Sun Shuttle. This sample is a live one, a real one. And so if you unzip it on your local machine, then it's very likely that your AV is going to complain and delete it. So be careful about that. All right. And this is it for the theory part of this tutorial. This is basically all the theory that we are going to, these are all the slides that we're going to have to suffer through together. And right now, I'm just going to switch to my my desktop and open IDA, and then we're going to get in there. Yeah. The password? Oh yeah, yeah. So there is a password. Maybe I put NorthSec 2023 with capital N, capital S. I'm not sure whether there is a space between NorthSec and 2023 or not, but this should be something either NorthSec 2023 or NorthSec space 2023. Either of those should work. If it doesn't, let me know, and I will create a new URL or something like this. I'll figure it out. By the way, if you have any questions at any time, I don't know if people can ask questions from the internet as well, but feel free to just interrupt me, raise your hands. We are in a, like, this is a small enough class, and I think we can have this sort of friendly discussion where I don't have to speak all the time. And if you have, if there's something that you are wondering about, feel free to just stop me there, and I will try to explain. All right, so let me just close down PowerPoint. And now I will switch to IDA. So the very first program that we're going to look at together is this thing, this very small sent to you. You should have the source code as well. It's really a super simple program. So even if you don't speak Go, which is actually my case, you should be able to figure out what this does. This is the sort of program I like to create initially when I get into a new language, because it evidences one of the most important things, which is how exactly function calls exactly work. So in this case, I just have a main function in the main package, which is the way that you define a entry point in Go language, as far as I know. And what you do there is you have a sum function that receives 3 integers and that returns an integer. And the only thing that this simple function does is return a plus b plus c. And here our main function will call this sum function and then print the result. And that's it. So super simple Go program. I point out that it has to be compiled with disables optimizations there, because otherwise the Go compiler is smart enough to just inline everything. And so you wouldn't see much. Now if everything gets inline, then of course, then you won't see your function call. And so that's not great. But anyway, let me start maybe with the very first thing I want to show you, and which is how exactly do we know which version of Go was used to compile the program. And it turns out there's a simple trick to do this. And I'm going to show this to you right now. I'm going to ignore this. So what I do is I open the program with the hex editor. Is this big enough for you guys to see on the screen, or should I try to zoom a little bit? Okay, I'll try to zoom there. So. Okay, should be better now, right? Okay, so this is just a simple hex editor. The one I like is called 010 editor. There are many different ones out there, so you really don't have to use the same one as me. But the only thing that I want to show you there is this super advanced trick where all you have to look for in the program is Go v1, I think, or like this, or Go 1 dot maybe. And you see, if you do, then you will find a string. I think it's the only one there. Yeah. And then you see Go 1.16.3. And so it's just there. And if you look at, as far as I can tell, all the Go programs that I've analyzed so far, if you just Control F, Go 1 dot, you will end up with on a string that contains the version number of the Go program. So it's sort of useful, first of all, to figure out if the program is written in Go or not, although this is sort of very obvious when you open it with IDA. But also if you want to know in advance what ABI is going to be used, and this is a quick trick that you can use. Anyway, so let me close this text editor because we're done with it. Now we'll just open IDA 64. A very, I think, a very telling thing is you see you have Go written there, and right next to it, it's work on your own. So basically, your IDA isn't going to help you much there. So let me drag and drop this here, open this Go program, and then it will take a bit of time because those binaries are kind of big. But as you see here in the function window already, IDA is able to figure out a lot of functions, format, PTR, whatever, actually, it doesn't matter too much. But as you can see, IDA recognizes the function names. In the past, as I mentioned, this is something like that. I have seen cases where IDA was not able to recognize this pretty well, but usually if you update IDA to the latest version, it tends to fix things, right? So if you open a program and you don't see any function recognized like this, just update IDA if it's possible, and then things will be better for you. One of the things I want to show is this. You see this very simple program that I had there. It looks like it's, I don't know, 16 lines big, not that much. It ends up being compiled as a 2 megabytes binary. So that's a lot. And let's see exactly what's in there. So you have many, many functions. All these functions come from the Go runtime, and we don't need them, basically. One thing I've sort of noticed is that the developer functions, they tend to be put at the end of the list, at the end of the binary. So if you are opening a program at random and don't really know what to start from, just take the slider all the way down, and usually at the very end. It tends to be the case. Also, you will notice that the names that are given to the package, for instance, we had this function sum there from the main package. And if you go back to IDA there, you will see that you have a function named main underscore case. This is a way in IDA to see exactly where the functions are coming from. So you do get the package name, and it sort of helps you figure out where the in which package. So I have to share again. All right. Are we back? All right. So let us start directly from this main.main function. Usually, as far as I can tell, the entry point of a Go program is always this main.main, so that's helpful. And let's see here exactly in this function where is the code that we wrote. So we do recognize this result equal there, so that much we can recognize. But already, it looks very different from the code that we had initially. Now, your intuition might be to just press F5 and try to see if maybe the decompiler can help you. It's not too bad there, but as we will see later on, it's not usually that helpful. Yeah, so it turns out that for this simple example, the decompiler is actually not doing too bad, but as we will see in the next example, it's not really usable at all. So let's forget about the pseudocode for now, and let's try to see exactly where the first line of our program was. So the first line was a call to this sum function there, right? And it turns out to be here. So it means that probably well, these are the arguments being pushed or being given to the program, but everything that came up above, all that, and also this, is actually stuff that was added by the compiler, right? This structure there is, or it's not really a structure, but this construct that we see, move RCX, GS28, etc., plus going here, is something we see very often in Go programs. It looks like they are, I think it's related to making sure that the stack has enough space for everything. Basically, we never ever have to worry about that. So one thing I sometimes do is I just color the blocks like this, just to materialize the fact that I don't care about them. So everything here, we don't care about too much. We don't even have to look at it. It's just stuff added by the compiler and will never have any impact on whatever we are doing in our analysis. So let us see our function call there. So we have this placement of all our arguments, 1, 10, and 100. You see here we had the call to the sum function with arguments 1, 10, and then 100. And so here they are being passed onto the stack there. Now, IDA is not doing super well already because you see that you have this offset related to RSP. You don't really like to see this, but okay. One of the things I want to point out is that here you would be tempted to rename this var88 something like arg1, something like this, right? Or arg_sum1. Because when you're reverse engineering a program, and what you want to do is you want to rename things, right? This is the way that's supposed to work. You recognize something, rename it, and then you move on. And then when you have renamed everything, then hopefully you understand what everything was and you understand what a program does. Now you will notice that unfortunately, this variable there is actually being reused somewhere else, and maybe somewhere there as well. And it turns out that these future uses have actually nothing to do with this initial one. It's another thing that is super annoying for us with the Go language. It's the fact that when there are regions on the stack that are not used anymore by the program, then the Go compiler is happy to reuse them again for other stuff. And that means that if you rename a variable sometime at some point in the program, then the next use might not be the same at all, right? It might be used for something different entirely, because the compiler is being smart about it. And so renaming things is actually going to be totally useless for you. And it's very unfortunate, but it is the case. And this is a simple example there, but you will see later on, when the functions are bigger than this, then any position on the stack may be used for 3, 4, even 10 different variables. And so renaming them, it's just not going to lead you anywhere. So one of the things you can do, instead of having those names that are just confusing and useless, is right-click. I think, I don't know if you can do it with, yeah, I think the hotkey is K there, or it's right there as well. You can just delete the variable names, and you can use just the offsets directly. Like you see RSP, RSP plus 8, RSP plus 10. You don't have a variable anymore, but it will make following things around a bit more easy. Because anyway, renaming things is not going to be useful, so like, why bother? I do not recommend that you go through every single variable and do this, because it's going to be very time consuming. But when you're beginning and when you are trying to figure out where things are in the program, then at least, it turns out that RSP plus 60 or plus 70 is going to be more meaningful than any name that you can put there. So anyway, let's see exactly what happens. So we have this argument number 1 pushed on RSP, so on the stack, or it's not a push there, but they just move it directly at the correct offset, RSP plus 8, RSP plus 10, and so on. So of course, this is a program compiled for x64, and this is the reason why all of our integers have a size of 8 bytes. So let's get into our sum function. So here, sort of simple. In this case, IDA is able to recognize the arguments, and you just put arg0 into arg8, add arg8, add arg10, and then you notice that the return value is not being, well, it is in rex, but it's not being returned through rex. It is just pushed back on the stack. See at RSP plus 20. And then when you go back, you see that RSP plus 18 is being moved back to rex. So maybe I should explain a little bit there. So this is the return value, but after you return from the function, this return operand is actually going to pop a return address from the stack. So this is why you have a difference in offset between the two function calls. Is that okay with everyone? It's sort of a not super important detail, but it's kind of, I just want to remind you that the offsets that you see in one function are not going to be the same as the one you see in the calling function, because between the two, due to the function call, due to the return operand that retrieves an address from the stack, the return address, then you will see an offset. And so even then, trying to recognize the numbers is not going to work. But the good thing is we're not going to bother too much. Anyway, so what happens next is kind of very difficult to decipher. You see that like when you start using the XMM registers, there is this type being loaded into REX. It's a structure. We won't bother about this one at the moment. We do see our result string somewhere here. Yeah, there it is. And by the way, one thing I can mention here is that strings in Python, in Go language, they have this structure where you have two fields. The first one is a pointer to the it's a pointer to the actual byte data, and it's followed by a size. So you see here you have a pointer to some characters somewhere in memory, and the size of 9, which is 1, 2, 3, 6, 7, 8, 9. So the size of the string. Yeah. So if you go here, there you will see all the strings of the program that are being grouped together one after the other. Okay. It's sort of a detail, so let's not worry about this too much. But you will see that here already figuring out what is happening there is kind of difficult, right? Where like the line that we have is this format.println result equal and then res, and it translates to this very complex series of calls there with the creation of a string type, a conversion to maybe an integer type. There you have this thing that was nowhere in our initial code. See this runtime write barrier, we did not write that, right? It's not in our initial program. So this is more stuff that the compiler added. I think it's related to garbage collection. We don't have to worry about it too much because it doesn't have any influence on what the program means, but it's there and it's sort of getting in the way. And then you have all this very weird moving around stuff here on the stack, in and out. And already we can see that we are reaching some sort of wall of complexity where trying to track every single position on the stack is going to be extremely difficult. So we will have to find another way than just to try to understand any single instruction, because I don't think there's any way, I don't think it's humanly possible. At least it's not possible for me to track everything. But we do, at the end of the day, see our format.println call, which corresponded to this here. All right. So our first encounter with compiled Go programs was, I would say, a little bit frustrating in the sense that we were able to kind of see what we had written initially in the program, but also there are so many things taking place that it feels like if we were looking at an unknown program, then we would not be able to follow through. Right? So let us look at another one and see if this intuition does confirm itself. So I'm going to show you example number 2, and you will see that this example number 2 is sort of the same thing, right? It starts with a main function, but this time our sum function, it doesn't just return an integer, it returns an integer and then a string and then an error, which is like returning an error, as I mentioned, is something that most Go functions do. This is the very Go way of doing things. So the sum function returns a plus b plus c like earlier. It also returns hello. And finally, it returns a new error, which is a, I don't know, whatever, a fake error. And now our main function is sort of the same as before. We call this sum function get, and we collect all the return values. And then if the error is not nil, we do print the string and the result. That's it. So it's not that different from what we had earlier, but you will see that in the assembly, what was already pretty complex now becomes frankly impossible to read, as far as I'm concerned. So let's check it out. Again, I'm loading the program. It's going to take a few seconds for IDA to go through everything. I guess I can already go in my main.main function. All right. And here, if you press F5, then you will see that you start having undefined values, undefined variables that do not appear to be created anywhere or initialized anywhere. Is because IDA doesn't really like having stuff coming from the stack like this, as far as I can tell. And of course, I mean, there's always going to be this sort of hard limits where you cannot represent a Go program as a sort of pseudo C code at all, because this context or this concept of having multiple return values just does not work. It doesn't translate in C. So you see there, you have this main.sum call. It's supposed to get 3 return values, and then you see that IDA is really not able to see that there are actually return values being collected. In some cases, I've even seen IDA miss out entire lines and entire function calls. So honestly, if you are going to work on Go programs, I will recommend that you do not ever rely on the pseudocode, because it just doesn't work. It really doesn't. So we will have to make do with our disassembly there. So we see at the beginning of our main function the same thing that we've seen before, which is, first of all, this sort of setup with this function that supposedly verifies that the stack is big enough. We do have the same thing that we had before, which was the passing of arguments to our main function. But this time, you see that it's being passed through registers. The reason for this is that this time, I compiled this function with another Go version. Let's check out which one. So I'm just going to open my trusty hex editor again. Control F, Go 1 dot. Oh, right, text. Yeah, and you see this one was compiled with Go 1.18. This is a more recent version. And so this is why this new function that we have here, this new program, actually uses the register-based API. So this way you can see both of you have seen both of them. So this time we move 1 in EAX, 10 in EBX, and 100 in ECX. So again, passing the arguments that were here. Then we call our sum function, and supposedly we're supposed to get 3 return values collected from this function call. So we have this call to the main.sum function. We will get in there in a bit, but then you will see that when we come back, then we have RAX, RBX, and RCX, in which the return values are being stored that get moved back on the stack here. And again, like, you might be tempted to rename this to what was the to res, but if we were to rename this to res like that, then you will see that later on, let me highlight it. Oh, it doesn't get reused this time. Okay. But in any case, this is not going to help us too much. Now, if you see here, already it feels like there's no way we're ever going to be able to follow that, right? We had a very simple main function that was 4 lines. I mean, 4 lines is not that big, right, supposedly. And it ends up being this huge monster of values being moved around, being, I don't know, translated or converted into various things. And just following this is a nightmare. Like, personally, I gave up a long time ago. So let's think of a way that we could do this a little bit easier. And to do so, we are actually going to move on to our real-life malware sample, which is Sun Shuttle. Just check out if there's something in this some function that is worth showing. I don't think it's the case, but we do recognize some of the stuff that we have written, like this creation of a new error object, this creation of our hello world string, one way or another. But overall things, this is the reason why most people, when they encounter Go for the first time, they tend to give up, because, I mean, it looks extremely complex and in ways that are totally gratuitous, right? Why does it need to do so many operations? Why does it need to move so many things around on the stack just to do those simple things we're asking, right? It's a good question. And my solution to this complexity is that we're just going to ignore it entirely. We will just not bother with all those operations and try to figure things out another way. So with that in mind, let's move on to our next sample, which is Sun Shuttle. So here I already have an IDB for Sun Shuttle, so I hope I didn't leave any notes in there. I don't think so, because again, annotating IDBs for Go programs is not going to be super helpful. So we go at the very end of this function window, and you see that there are a number of functions there in the main package, and all the rest appears to be stuff that comes out of the I don't know, of the Go standard library. Let me actually show you something that's pretty cool. I mentioned earlier that there was this collection of plugins that were available on GitHub from the Sentinel-1 researcher, Juan Andres. One of the various scripts that is in this repository is called, well, what it does is it uses this feature of IDA where you can classify functions into folders. It was introduced now some time ago. It's not used that much as far as I can tell, but it's really a super useful feature. So the way you enable it is you can right click there and click show folders. But initially, of course, you have only a single folder, or everything is the same folder, right? And if you want to, you can then create folders. I don't know where it is exactly, I don't remember. Oh yeah, create folder with items and so on. So you can create folders, move the functions in there. It allows you to sort things out and to make them a bit easier to access. So what this script does is it will create folders for all the packages and sort everything in the correct folder. So I'm just going to, I don't think the script is present on your VMs initially, but I'm just going to run this on my own. And this is categorize Go folders there. I'm just going to run it. Hopefully it still works. Okay. You see here, it created all these folders and sorted everything according to the package. So I personally think it's super helpful because what it does is it allows you to take away all the various functions that come from the standard library, everything that comes from the OS package or the /lex package or whatever, and puts them away. So you don't really have to look at them anymore. And you see here that the only package that I'm left with, but there's this unnamed thing, maybe you can look at later, but even a real-life malware like Sun Shuttle, you see that at the end of the day, the only functions that we care about are those ones, right? They appear to be the only ones that were written by the malware developer. So that's pretty cool. It means that although we have this 5 megabyte binary, I think, Yeah, exactly. Even though we have this 5 MB binary, we actually only have something like, I don't know, let's say 20 functions to go through. And that's not that much. Now, of course, the functions that we've seen before with our Hello World examples hinted that it might still be a bit of work, but let's see how we can tackle this, right? So we are here in our main function. You see it's quite big. If you look at the window down there, the graph overview, you can see it's pretty long, so not cool. But let's see how we can work through this. First, we encounter the same thing that we had before, which was this construct and this call to runtime more stack no ctxt. So let's just ignore this because we don't care. The first thing that happens in the main function is a call to net.interfaces. So just the same way that our main function was renamed main.main or main_main, we have this function there that comes from the standard library, and which is the interfaces function coming from the net package. So what is it exactly? This is not something that the developers wrote. It's something that comes from the standard library. So let's go back here. You go to pkg.go.dev, or maybe the former URL still works. You look for the net package like this. All right. And then let's look for the interfaces call. All right, so there it is. Lo and behold, you get the description for the function. It's not that complex, really. It's a function that returns a list of the system's network interfaces. All right, so pretty easy. And let's look at the arguments. So no arguments for this function, as you can see there, but you do have here a the return values. So it returns a array of interface objects and an error. So what we are going to do now is we are going to try to recreate the Go code that the developers might have written to get to this compiled binary. And this is actually, well, this is actually easier than it looks. So let me just create a new program like this. So I'm not a Go developer, so if you are, then you will hopefully forgive my inevitable Go mistakes, but we'll do something that looks sort of like Go. Let's call this Go pseudocode. So let's call this package main, and then func main, and then brackets. And we start with a call to net.interface. This is like that. We know that the function takes 0 arguments from the documentation. And we also know that in Go, you are forced to collect all the return values. So it means that we have to do something like interface and error. We have to collect those two. So let's write something like interfaces, or and then error, and then the assignment operator in Go is colon equal. That's it. So when you see here this call to net interfaces, you can see before that whatever Go version was used there doesn't seem to be any arguments being moved to the stack or being passed around. So this is probably the line, the Go line that was written to get to this here. All right. So next, stuff is happening. So by now we know that just after the function call, we do see the return values being moved back from the stack to the registers. Okay. So what is going to be done with those? We don't really know. But in any case, what we see a bit later is we have this comparison between something and 0. And then depending on what happens, we go into this block or we skip it. Okay, so here, I could try to figure out exactly what is inside var underscore d0. And probably if I were to open a whiteboard somewhere and draw something to represent the stack, I would be able to figure out things. But I'm just going to do a bit of guessing here and think about, as a Go developer, what would be the natural thing to write there to compare with 0. Well, based on what we get there, I think the very natural thing to do would be to do something like if air equals nil, then we do something, and otherwise then we don't, right? This is what the Go language wants you to do, right? You call a function, you get an error object, and then you test this error object against nil or against 0, right? And so let's see what happens if we go into this green green branch. And so it means if this thing we tested was indeed 0, then we just have this call to OS exit, and we put an argument which appears to be 0. Now, one of the things I've noticed with the Go language is that it really tends to group all the arguments just before the call instruction. So when you have a function call like this, then immediately before you will see move argument to the register, move argument to or the register of the stack and whatever. So if you take any call, then the instructions, this is something that I've seen to be consistent across most Go versions I've looked at. So it's pretty cool. It means that, well, if you take a language like C or C++, sometimes the arguments can be moved on the stack way before the actual function call. In Go, it doesn't happen, or at least as far as I can tell. So if you take any function call there, then immediately above you will see the arguments. So the argument of our os.exit function call is going to be 0. Now, I could pull up documentation there and go see exactly what this os.exit function is. I think it's going to be obvious to everyone. Let's check how many arguments it takes anyway. Okay. So there it is. So function exit, it takes one argument, and then it exits the program. So let's go back here. So if our object, which I assume as error, is different or is different from nil, check. Yeah, it's probably this. Then we go there and we call os exit 0. So let me update my code there. So if we have an error, then os dot capital E, and that's it. So as you see here, like, I'm not really looking at the assembly too much, but just with educated guesses, and just by looking at the various function calls that are performed by the program, the various library calls that are documented on the internet, I am able to sort of figure out what is going on in the program. And this is going to be my global approach, right? I don't want to have to track all the values as they are being moved around the stack, because this is going to take me forever, and I'm not sure I'm ever going to be able to succeed anyway. But just looking at the API calls, just looking at the arguments that are being used here and there, I'm fairly confident that I will be able to understand the global idea of the program. And if by some, if I encounter something that is a bit more complex, then I can just take out the debugger, which will be later, and I can just go and put breakpoints wherever I want and check out the actual values that are put into the stack or into the register, depending on the ABI, and I will be able to see exactly what arguments are being used to call to any given API function from the Go standard library. And it turns out that just by looking at the sequence of all these calls, I am able to reconstruct this sort of flow of the program. So let us move on and see how far we can go like this. So if we call os exit, I suppose that it doesn't really matter too much what happens after this, because the program terminates. So let's just skip over everything that is not a function call. The next one is here. And you will know it seems to be a loop. This is something in IDA somewhere down here. And at the end, we go all the way back up. So we have some sort of loop. Maybe it's for, maybe it's a while, right? And try to figure out what this loop could be. Now, based on what we know, based on what we have on the code so far, I think there aren't too many options there, right? There's only one thing that we could loop out. We could loop on here, right? What would that be? It would be our interfaces. Does it make sense to you guys? Yeah. So let's try writing some code. I don't know exactly how it would be written in Go. Let's assume it's like this. So for I in interfaces, and then we do something. And this something is going to be whatever happens in there until we loop all the way back up. Now, as I said, as I promised, we will completely ignore all this sort of nightmare of this horrible shuffling around of memory that is taking place there. If you wanna track it, be my guest, but I'm just not going to bother. Right? Let's just go directly to the next function call and check out what it is. This one is called net hardware ADDR string. So let's go back to documentation and see what it is exactly. So we go back to the net package. Okay, so hardware ADDR appears to be a type that represents a physical hardware address. All right, why not? So maybe what is happening there is something like this, right? Something that I dot hardware ADDR dot string, something like this, right? It's an assumption. We'll see how it turns out. Okay. And so here we do have. By the way, if you look at the documentation, you will see that it represents a physical hardware address function here. It just returns a string representation of our hardware address, I would imagine. I don't know if we have an example somewhere. It doesn't matter too much. But anyway, so we go back to IDA here, and the next function call that we see is this runtime mem equal. Now, I think it doesn't require too much guessing to figure out that this is going to be a string comparison. So let's see what we're comparing with. Just looking a little bit above, you see that we have this string that is in there. And you see that IDA is sort of not super good at recognizing where the string ends. So let's just go in there and see what happens. Now, you mentioned in the theory part, if you recall, I mentioned that all the strings ended up being garbled altogether in the program, right? This is something that I hinted at, and you see here exactly what I meant. You see that all the strings of the program, they are just, they're just there, one after the other, and there is no real way of figuring out where the string starts and where the string ends. This is kind of annoying for us. The way that the program works is whenever a string is needed, then the program forwards the you get a direct offset to the string inside this big string ball, I would say, and you have a size somewhere, which here is there. The size is 11H, so 17. And so here you would do something like 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, and 17. And so you get the pointer to the string somewhere, you get the size of the string, and this would be the string that we are interested in. And it makes sense because then this decryption, fail to enter, etc. seems like it's a part of some other string there, right? So what's happening there, we have this call to hardware ADDR.string, and then we have the comparison with this. So we can keep reconstructing our source code. And we can do something like this maybe, right? And then probably, if we have that, it means we are in the if construct. Okay, so what is this MAC address exactly? I mean, this, we can just do a quick Google search. I'm pretty sure that we are going to, end up with tweet about this incident, you will see that this is actually the MAC address for the Hyper-V interface from Microsoft. So this is actually some anti-VM protection in there. So the malware just checks if we have an adapter that has this MAC address, and if so, let's see. Yeah, we do have another call to os.exit. All right. So let's go back and complete our source code. Like this. Okay. So we are making progress. Let's go back there. And then, we don't have any more function calls, but just looking at the graph, it looks like we are just moving on to the next iteration in the loop. This is probably a check on the size or the number of iteration counts we want to go through, etc. And then when this is over, we go to this block there. Okay, so let's keep going. We have a call to time.now. So just a quick check. Is it okay for everyone so far? Are you following the general approach? Yeah. Okay. Great. So here we can get out of this for loop, I suppose, and we have this time.now call. Okay. No semicolon. Okay, so here you do have this weird value. As far as I remember, this is actually some timestamp conversion that is taking place. So the way that time.now, I think, does not return a timestamp on the Linux format, and this is just a conversion here. Usually, it's a good idea if you do have those sorts of constants in a program. If you want to know what they are, you just Google them. It's a good way of figuring out exactly what they are. Let's see if we the result there. So here we do have a bit of code that is dumped from whoever knows where. Let's try in decimal form. Okay. So I apologize for the results in French, but overall, what we see here is pages related to calendars. So we can guess from there, we can infer that this is related to whatever conversion taking place. So let's ignore that, because we don't really need to worry about that. If we just move to the next, function call, we see this mat rand ptr rand seed. If you have developed programs in the past, then it's going to look kind of familiar. It's something you probably have done whenever you were using cryptography or whenever you wanted to use randomness. And what they do there is initialize the seed of the RNG. So let me update the code there. Now, we don't exactly see how this result of time.now is being used, but again, with a bit of educated guesswork, we can figure out that this is probably being used to seed the RNG, because this is the type of code we see every time. So mat.rand dot seed. Right? Looks like something that makes sense. So let's keep going with this and see what happens. Now, the next function call is sort of interesting for us, right? Because this is another function that comes from the main package. So this means that this is not something we'll be able to look up online. It means instead that this is some code that comes from the developer code, the malware author written code. It's something we need to get into. Okay. So we get in there, and I think this might be. I don't know if we take breaks in the workshop. I think having a 10-minute break would be nice, I suppose, because it's sort of a dry subject matter. So if you guys want to walk up for 5 minutes and walk around, fine by me, right? So we take up again at 2:30. Is that okay with you? All right. So see you in a few seconds. Okay, come here. And no problem. Don't sweat it. So there is actually no VM, but there are two ways of. I mean, I will share this PPT with you if you want. I started with some general say information about the language. When it comes to this tutorial, so there are two ways of doing this. If you do have either Pro or Ghidra, whatever you're comfortable with, you can just download the sample directly and work on your own machine. If you don't, I do have some online VMs that you can log into through RDP.
I've got BinChat, so
If that one,
binary BinChat.
probably it works too. Yeah, so in that case, you can just go to kwi.ski or the full name there, and there's going to be just an archive there, and you can just download the sample and look at it. The password is infected. Yep.
What's the URL for the samples?
Sorry?
The URL for the samples?
It's here, p.kwi.ski. Or do you have
it's all the X's, that's fine. Great. I'm on Linux, it's not a problem.
Yeah, but you don't need to run them.
Oh no, I know. I just normally always, if I download a .bin, I always rename it to something that runs on my machine.
Yeah. Probably essential should be without extension. Oh no, that one. Yeah, not good. Yeah. The password is infected.
So that was probably a dumb question because I totally forgot. How do you actually run these scripts? Like if I just go and run a script file, it just doesn't do it.
Yeah, so that's the script I think has very likely worked, but there is one more, say a subtlety there is that by default the folder view is not enabled. So you need to right click there and maybe show folders. And there you go. That's the only thing.
It's working perfectly silently and then not switching over. That's great.
Yeah, no, I think that IDA should enable this by default. And at least if you use folders, they should be shown by default as well. In terms of UI, they have a bit of improvements to make. But in any case, it works.
Are you planning at the end of this to actually compile the code that you're writing and then do like a side-by-side comparison?
I won't do it, but this is what when I was beginning with this, I did. So I would take the same Go version, compile the code, and then look side by side to see if I was close enough. And if you take the same version of Go, it will generate the same. If you have the same code, it should generate the same binary at the end, or the same functions. So when you start out, then you can compile the code that you write on your own and then see if it's kind of the same. If it is, then it means you're on the right track. If not, then maybe some subtlety or something different that you didn't take into account.
I feel like I might wait until I'm home and I have a monitor set up.
Yeah.
But it's cool.
Thanks. Let me comment.
Previous question. So if I want to build, because that seems like it's go 14 points.
Let me check. It's an old one.
Yeah, the central looked like it was 14.
It's very possible. Yeah, 140, not 2.
Do I have to, like, go to Debian package sites and go back and pull 14.2? Is there a better?
There's a simpler-ish way, which is to get the official, to build Go yourself from the sources.
And just check out to the version you need. They're all properly typed and stuff.
They are, I think, if you go to the Go website, you can probably download you can maybe download the old versions individually. If not, you can get the source code. I would not recommend deploying the dev packages on the system, because you're going to end up with broken dependencies possibly, or with an old Go version that you might not know what to do.
I would just extract them to a subdirectory and see if I can run it from there. Not actually install it.
Maybe. But in any case, on the Go website here, you have all the archived versions like this, and you can take any of them. You get the source code, you go in there, you compile it, and you're good to go. Supposedly.
That's a bit bigger project these days.
Yeah. Let's go back. All right. Okay, so I think we're probably almost ready to resume. Are there any questions about what we've seen so far? This is not, you can feel free to ask any questions during the course of the tutorial, but if you have some now, I'm happy to take them. Right? No? Okay. So let's just move on. So before this break, what we had done is we had just reached this new function that was also a function created by the malware developers. This function is called define interval settings. So the script and just create it as well. Define interval settings. I don't think it takes any arguments. There is one way to find out, which is to go back one step and see if there are any arguments being passed to it. Doesn't seem to be the case, although here I will draw your attention to the fact that with Go, the way that arguments are being returned is a bit tricky, in the sense that they are placed exactly where they need to be given or reused as arguments for the next function. So if you have this call there from this seed function, then whatever argument it returns is already in the right place to be, whatever return value it gives is already in the right place to be used as an argument for the next there. The seed function does not return anything, but this is, I think, a smart way that the Go developers, the Go creators devised so that function calls can be chained in a very efficient fashion. Anyway, so here we don't, it doesn't seem like we do have any arguments to this function. So, all right, let's add the brackets. And so the first thing that we see here, again, ignoring all the crazy memory operations, are strings that appear there, config.dat, and then .tmp, and then this concat string. So this concat string is string concatenation. Yeah. Well, you cannot know in the sense that the stuff is placed in the right position already, but then whether or not it will be used really depends on the next function, right? So the only way you can know is if you look at the documentation. If you look at the documentation and see that the second function, for instance, expects 2 arguments, then it means that probably whatever comes from the previous one is going to be reused, right? Then if it's a custom function, it's going to be a bit more tricky, right? So usually this type of function .something really comes from the stamp library. Like the developers, they don't do that too much, as far as I've seen, but it may happen. And if it does, well, you're on your own. Maybe you can find, one thing you can do is maybe, with you can press X, find all the cross references to the function, find another use of that function where it's not chained like this, and then see that instance if it's taking something from the registers or from the stack. That would be my best guess. Okay, so here the first meaningful thing that appears to be done in this function is concat string of tmp and config.dat. So sure, why not? Let's do s equals config that plus tmp. Like, of course, we keep in mind this operation because we know what it does. And then we have this called io.util.read file. Okay, so we can guess very easily what this does, but at the same time, let's check out the documentation to see what the arguments are and so on. So let's go to the IO package and then read file. IO util. Okay, so this function, as the name implies, reads a file. What it does is you give it a file name, it returns to you all the bytes contained in this file, and then, of course, an error object, as is tradition would go. So here, I don't even have to open IDAV again, I think. I can just do io.ioutil.read file. And it doesn't take too much guessing to assume that what argument is going to pass there is going to be this function name that was given to us. And also, let's take the return values. Contents and also air equals this. All right. Moving on, we see the very traditional just after function call a check between something and 0. So again, we can take a guess and assume that it's our error being tested. So let's do that again. If error is different from nil or something, and otherwise, we'll see. Now, we do see that earlier one branch was super easy because it was just os.exit. In this case, it's not really what happens. So what we can do is let's start by following the red arrow, which is going to be the one that is called or the one that is followed if we do not have the file present on our system. Because at the moment, this file here, this file called config.tmp. We don't have it, right? We don't know what's in there. So let's assume it doesn't exist and see what happens with the program when that is the case. So we go into this block, and then we move on. We have this os.open file. And here we are going to need to see the arguments again. Okay, so this function opens a file, of course, and then you have 3 arguments: string, an integer, which is the whether the file is created or read-only, that kind of stuff, and then a permission. Okay, so let's see here in IDA, the file name, I assume, is still going to be our config.dat.tmp being passed away from above. This is something we can check. This is something we'll check in the debugger, actually, because it's starting to be, we're doing a lot of guesswork, so it's good to backtrack a little bit and check if we are on the right track. And here, if you change this to octal, I think, yeah, you see that this is a creation of a file with permissions 666. So, the read write, execute, maybe, I'm not sure, at least read write. And the final one, I'm not sure, this should be create. Right? You can check the flag and try to locate where it is exactly. Okay, so let us open this program in the debugger and check that we are still on the right track. So what I have there is I have a VM, and in this VM I have my debugger, which is x64dbg. So I'm just going to drag and drop this program here into my VM, give it back the exe extension. And there are going to, before I even do this, there are going to be a few tips and tricks I'm going to share with you. The first of those tips and tricks is that one thing I love when I'm debugging is being able to copy addresses from IDA and put breakpoints directly into the debugger, right? Because it simplifies things a lot. Like if you press space, you have the addresses here in the margin, for instance. And let's say I want to put a breakpoint there, I would just copy this address and open this in the debugger, paste the address, and put the breakpoint there. Like the issue is, due to the ASLR protection that we have in binaries, then my program is liable to be loaded anywhere, right? And that's super annoying for us. So there's actually a way to circumvent this issue entirely. And this is thanks to a small utility from a guy called Didier Stevens. It's called set dialog characteristics. You can find it online for free. Let me show it to you. So this is a small binary that you can use to edit the header of a PE file. So for instance, whether a program is compatible with ASLR is shown inside the binary by a flag somewhere. And so if you just change this flag in the PE header, then the program is reported as not being compatible with ASLR. And so it will always be loaded exactly where you want it to be. So this is a pretty cool utility. I do recommend that you have it somewhere because it's super useful. And the way it's used is very extremely simple. So in my VM, and if you are using my online VMs, it will be in the same place. It's in C/tools, and then set dialog characteristic, and then it's -d, and then the program. Minus because you want to remove it. You can do +d if you want to enable it as well. Like this. And there you go. So you see they updated the dialog characteristics and they disabled ASLR. So that's pretty neat. It's pretty useful. So this will allow me, thanks to ASLR being disabled, to copy addresses from IDAPRO and then use them directly in my debugger and save me of having to convert them manually and to do this translation and so on. So that's something I suggest you do. It's not just for Go binaries, by the way. Whenever I have to debug a program, I go through this step because it's so useful. So let us open this program with x64dbg. And you will notice, oh, maybe I should zoom in, not there. Let me see. Yeah, let me just increase the fonts a lot. Okay, so I will assume that all of you are familiar with debuggers. I don't know if you used this one before. If you do have questions about it, feel free to ask. One of the things that I want to show you too is that, well, when you move around in the program, you will see that, for instance, let me put a breakpoint exactly where I want it to go, just before this open file call. Okay, so to copy this address, go there. And you see here, there's one thing that is actually a bit sad. It's the fact that this call there is equal to sunshuttle.4bd630, which is, of course, the address of this function in my program, but where IDA Pro was able to, like, through X-rays, dark magic, to recognize that this was the Go function, io.read file or open file or whatever. The debugger does not have this intelligence programmed in. It's not able to parse the Go program and to recognize function names and so on. But as you can imagine, it would be super cool, right? If we were able to import the names that come from IDA and put them inside our debugger. Turns out this is actually possible. And the way you do this is with a plugin, x64dbg IDA. You can find this on GitHub. And there it is. Yes. Sure. So let me just go back to the binaries. This is the tool that you need. And well, then it's super useful. You just do set the other characteristics and then the file, and then an option like +D activate ASLR, -D deactivate ASLR, +N activate dep, -N deactivate dep, and so on. Exactly. Maybe it's already open in the debugger. Oh, maybe it's possible. Yeah, I think I disabled. Well, on which VM is it, on yours or on the one online? That normally inside this, it's supposed to be in a folder where the AV doesn't go look. Oh, then you will have problems with the AV. Yeah, no, that's not going to work. The AV is going to break things for you. So you have to, you have to either copy in the same folder or just work in the original folder. Now, the VMs that I shared with you, you can actually revert them when remote. You have this toolbar on the top. You can just restore them to the original state. So don't be afraid of breaking them. Like, it's going to take some time to restore, but at least like you cannot cause any lasting damage. Anyway, going back to our debugger there, you notice that this call to some random address is not really helpful to me. And I would like to import stuff. I would like to import my names from IDA into my debugger, which is something I can do thanks to this repository there. So again, if you're using IDA, this is the plugin to use. If you're using Ghidra or anything else, you're sort of possibly on your own. Sorry about that. But I'm still going to show it to you with IDA. In your VMs, you can either import this script, you can download it and copy it inside your machines, or if you're using my VMs online, the plugin should already be set up. And in IDA, what you would do there is you would do edit and then x64dbg IDA and then export database. And this is going to create a big file. Actually, let me launch it right now because this actually takes super long. So let me put this on the desktop. Some shuttle. And what it does is it creates this big JSON file that contains for every address a corresponding label. So you see there that it's going to hang for a while, and this is because the binary is so big, right? There are probably tens of thousands of names to export. So this will take probably something like 30 seconds, and it will be exactly the same on the other end when we import it back into x64.bg. Okay, so there we are, hopefully. Right, so I do end up with this sunshuttle.dd64. You see that the file is 85 megabytes big. So all the names have been exported here. It's something super, super huge. Anyway, I'll just put it in the VM. There it is. Another thing that is a bit annoying is the fact that in order for this to work, the program in the VM needs to be have exactly the same name as the program in the host. So it means that if the program that IDA is analyzing is called sunshuttle, then the program in the VM has to be named sunshuttle as well. And you see here, I have this exe extension that is going to cause a problem. So this is something that happens a lot. Usually when you work on a program on your host machine, you take away the extension. You don't want the exe extension to be there in case you double click and infect yourself. And when you want to run the program in the VM, then you rename it to e.exe. So how do you solve this? Well, it's sort of easy. You just open the database there with a notepad. Notepad doesn't really like having those big files here. 85 megabytes is a little bit for it, but you can just rename this module name and rename it to what you want. So I'm just going to replace this to sunshuttle.exe and replace all. It's going to take a bit of time as well. The reason why we need to do this is that if you don't, when you import all the database into x64.dbg, it will import all the names properly, but it won't be able to recognize that the names match, are supposed to be associated with the binary that you gave to it. So it's sort of annoying, but yeah, we do have to do that. So I'm going to wait a little bit for this to complete. Again, this is a very big file, so the replacement is going to take some time. And then when this is over, I will go there on the x64.bg and just do, where is it actually? Oh, database and then import. Not done yet. Let's wait. In the meantime, one thing we can do is at least we know here that we have a breakpoint on this open file call. So we can look at the arguments and check exactly what they are. It was the whole point, right? So here this argument is 666 in octal, but what we want is the file name. So the file name is RCX. You can just do right click here. All right, it's fine. Okay, so here I have reached my call to open file. This is still running, this is taking so long. Okay, so here I put the breakpoint on my open file function, and it's very easy for me to go back up and look at the arguments. And the argument number one, if you go back to documentation here, there, argument number one was the string. And so if you recall, I mentioned that the string was a structure in Go, and the structure is going to be a pointer and a size. So let me take, so RCX there is 0E. RSP there is config.dat.tmp. Okay, right. So you see that you have this config.dat.tmp, which is put on the stack, and then the size of the string put on the stack as well, and then the other argument. So it's kind of difficult to track down, but overall, you can see that here, when we reach this open file call, this config.dat.tmp is still there somewhere. So let's update our code here. I suppose it was something like O_38 or something, and then 666. And from now on, we're going to be using the debugger a bit more, provided, okay, great, this is over. So I'm going to save that, and I'm going to import my database there. So again, you can do file, database, and then you can import whatever you put in your VM. So to do this, it's also going to take some time because it has to parse this huge file that is 80 megabytes big, but eventually, oh, there you go, you see, now in x64 DBG, I do have the correct names, like sunshovel.os.openfile, etc. So it's going to make my debugging experience a bit more enjoyable. All right, so let us ignore the debugger for a second and go back to here. So we know that open file returns a file and an error. So let's update our code again. F error equals that. And you see that this time they don't seem to be checking this error object, which is bad practice, but it happens. The next thing they do is they do this time.now and then time.string. And this is one of the examples where it looks like this chaining of functions is taking place without having to move the arguments again. So we have this time.string. And it's being applied on time.now. Okay, so moving on. And then we have this call to get MD5 hash. Well, the name is kind of transparent here. It's fairly easy to guess what is going on. We can go in there and check very quickly. Actually, we will get back in here in a second. Let us just here look in the debugger what is being passed as an argument, just to make sure. So let's put a new breakpoint over there, move forward, and here you see that whatever is being passed as an argument appears to be indeed the timestamp of the current date. So we are doing still a little bit of guessing, really a lot of guessing even, but we're still on the right track. And we can also skip over this function and check out what comes out of it. Let me just follow this up and copy everything. So I'm going to copy all this. And since I do believe that this get MD5 hash function is going to calculate an MD5 hash, I'm just going to verify that this is true by calculating it myself. Let's go to CyberChef. I don't know if you are aware of CyberChef. I assume you are. It's a very useful tool that you can use to convert byte, convert strings, and encode them, decode them, etc. It's really some sort of Swiss Army knife of all the various encodings and data transformations you can think of. So it's super useful. I don't know why it's so long to load, but guess they want us to see their funny messages. Fine, let's go back to the page. So this is where we are, and we know that we have this main dot get MD5 hash. Like this. I'm just going to put this here. Come on. And then here, I'm just going to press F10, F8, skip over, and you can see the return value right here. Here, the value you see in one of the return values, you have 20, and the other one you have a hash. 20 is 20 hex, so 0x20, it's 32 bytes, and it's exactly the size of an MD5 hash. So normally what we would do there is I would verify that this hash value, I'm fairly sure this is the case, so we're not going to wait until CyberChef loads. But this would be a good way to not have to reverse engineer this function that we are looking at here. We wouldn't have to go in there, we just know what comes in, we know what comes out, and then we can figure out what it does. One thing I want to show you here is that sometimes, it's not very often, but sometimes you have this, in Go, you do have this runtime new object, the call taking place. So it's whenever you do have a class instantiation in Go, and it's something that IDA is not able to handle too well. The way it works is you pass a structure here, which you cannot get into because it's, I'm not saying it's opaque because it's documented, but you cannot read it manually. And you pass this structure which describes a class into runtime new object, and then in return, you get an instance of this class. Now, I wrote a script that resolves those types, because actually all the type information is hidden somewhere in the binary and you can find it. So I'm just going to run that script. It's also in the repository I mentioned at the beginning of this presentation, and the one called AlphaGo. So you would get script file here. It's the number 5 extract types, and run it. Hopefully, yeah, there we are. And then you have a type which is a pointer to an MD5 digest. So you get this type, pass it to runtime new object, and then I guess you use it. Here, I'm going to skip a little bit over things. You have this stuff pushed into the MD5 digest. You have this C digest write, and then sum, and then finally encode to hex. So it really is something that looks like a traditional creation of a MD5 hash or a computation of an MD5 hash. But that's the very cool thing. The very cool thing about Go is that if you were looking at a C program, then you would have to recognize the constants and try to see how the hash is calculated and so on. Here with Go, we just have to look at the calls to the Go standard library. We can see that we have calls to first an instantiation of this MD5 digest type. We have then a call to this digest write, digest sum, etc., and then encode the result, and that's it. So this is why I say very often that I think Go reverse engineering is quite easier than other languages. It's just because you don't have to recognize anything. You don't have to work with crypto. You don't have to get into complex functions. You just have to look at the calls and see how they are chained together, see how they relate to one another. And from there, you can just reconstruct the meaning of the program. You really don't have to invest any effort in recognizing what is happening in any function, really. Maybe one thing I can explain there as well is this string to slice byte is a way to convert a string to a byte array, the byte array corresponding to the string bytes. And this one, make slice, is a function that returns a subdivision or a slice, I think it's called, the subdivision of some array. So this is what it's used for, but I really haven't seen many cases where I really needed to figure out which slice needed to be caught or exactly what part of the array was being taken away. So when you see those string to slice byte and those make slices, etc., it's really usually the compiler making sure that the types can get converted properly from one another. All right, so let's go back here. Did CyberChef ever load? Yes, it did. Wonderful. So let me just get this there and make sure that everything works as intended. So this is my input. Let's take MD5. Come on, how can it be that long? Jesus. Oh, well, I guess we'll be back in a bit. Anyway, we calculate this MD5 hash. We need to have this runtime GC write barrier, something related to the garbage collection. We can skip over it. Okay, and then we have more stuff. So this string, which looks like a user agent, and then base64 encode to string. All right. So this is very likely going to be encoded, etc. So let's take things. So let's go back to our debugger. Put a breakpoint there and see what happens exactly. So I'm going to run until my next breakpoint. There I am. And so here, see that the string is done. This user agent that we saw somewhere in the code. All right. And then very likely, if I press F8, what comes out is going to be base64. One thing I can point out there, let me show you the documentation for base64 encode to string. Because there's something interesting that is done there. You see that the MD5 hash of this string was C4, so our hypothesis was correct. Okay, let's forget about this for a second. And let's here to base64. And then the function we are interested in is encoding and encode to string. Now here, there might be something you would be wondering about is the fact that, okay, we know that we have this encode to string function. This is the type of the arguments. This is the return value. So what is this, right? What is this extra thing that we have there? This is something that in Go is called an object on which the function is applied. So in the case of base64, there are actually different encodings. So you see here you have base64 std encoding and then string, and there's another one which is URL encoding. So it's actually a different alphabet there. And so you would have to be careful there, because normally this would never be an issue because everyone uses the normal encoding of base64. Well, in this specific malware, they actually use both encodings. So they use the base the URL encoding as well. The way that you'll be able to there, which represents the encoding, and work your way back up in the code. Anyway, this is just a small detail. But if you try to decode, and show this to you, if you take this result here in base64, and if you try to decode it, you will see that, well, maybe for this specific string it works, but for some strings later on it would not work because it would contain characters from the URL alphabet and not the standard alphabet. format int, which is a function that is a way to convert an integer into a string. And there you would see that this is this string there is going to be the integer that's being converted. So the integer is 5. Now, normally I said it's useless to rename things in Go. Well, for global variables, it's a bit different because, of course, the global variables, they tend not to be, well, they do not get reused, right? So at the moment, we don't know what this is, but let's call this global int 5. And it gets converted into an integer, and you have a number of these taking place, right? Then you have this here, which is 0xf, so 16. I could rename anything. All of this, I'm not going to do it. You see that we have a number of them being converted like this. Okay. So I'm just going to skip over to the next function call, and you see there, whatever was going on here that we just skipped through, all those strings that were being created, they end up being concatenated at the end. So we are just going to copy here. We're just going to copy the address. And now with the debugger, we're just going to look at the end result of this whole string concatenation. Again, I'll go back to the debugger, Control G, Control V. I'm going there. And here, the end result is this huge string there. So I'm just going to copy everything. And so you see that one way or another, this huge string has been created. So we have first this, which is a hash of the current date that we know because we've seen in the code. This 5-15 is something that was constructed out of these hard-coded integers, same for 0, 0. This is a user agent encoded in base 64, and that's it. So let's go back here. String to slice bytes to just conversion. Main.encrypt, that's interesting. I'm going to skip over that for a second, and then write file. So let's recap a little bit what we've seen so far. Maybe pull up the code that we were writing. You see, I kind of gave up on doing this reconstruction of the source code. I'll say a few words about that later. But generally, the idea there was this. We have this function called define internal settings. There were two branches. One of them was if this config.dat.tmp file exists, then something, we don't know what happens there. Or if it doesn't, then the file is created. Then we generate this whole string there. Then we have a call to main.encrypt, which I'm going to comment here, / stuff. And then let's assume we end up with S config equals something like that. This. And then we have main.encrypt of, I assume, config. And finally, we had os.write, right? Main write file, which I guess, yeah, open file, string to slice byte, file write, sync, close. So yeah, just a wrapper around wrapping stuff, around writing stuff into a file. So let's do this. And here I'm just going to go out on a limb and guess that the arguments are f, which is the file we have there, and config. Okay. So in essence, if we end up in our branch where this read file string does not exist, if our file name config.tmp does not exist, then we just enter this branch, and then some sort of default configuration is generated from the program, from the hard-coded values present in the program. And we know that this is going to be, this is a timestamp, or the hash of the timestamp. These values we can maybe figure out later on, and this is an encoded user agent, and that's it. Now, let's check out what is going on in this encrypt function, I guess. Right, this is going to be our next step. I'm going to go back up a bit. Oops. Not too much. So we skip over this. So you see that now I'm starting to play a bit loose with my reconstruction of the source code, right? I'm taking shortcuts, and I'm not really doing as much as a rigorous job as I used to before. It's because when I actually work on a Go program, then I'm not really going to bother doing all this all the time. Right? The first time I worked on a Go program, I really reconstructed the whole thing like that. And I really encourage you to do so when you are starting out. But of course, as you move on, then you're going to start figuring out what you want to program. You don't have to write everything the way that you used to in the past. But I hope you will believe me when I do say that when I started out, this is actually what I did, and this is how I really got into reverse engineering Go. So it's a method that does work. When you look at me doing this, it's very, I suppose that you will be tempted to think that it's sort of easy because I've looked at this program before, and so I know what is happening and I know what the source code is supposed to look like. But actually, like, this is really the way that I approached this program initially when I first encountered it. Right. So let's go into this main encrypt function. And there again, we're going to move very quickly through things. You have this crypto AES new cipher, creation of an AES cipher. Bytes repeats there. I'm going to assume this is maybe some padding or something. Okay, runtime grows less. We don't care about that. Move, make slice. Not much is happening there. IO read at last. Now something interesting. Cipher new CFB. So the cipher is going to be AES. I think. Did I see AES before? I think. Yeah, AES new cipher. So we have an AES cipher. Now we know it's in CFB mode. So we have to skip over all the stuff. And some encoding in place. And yeah, so what's going on there? So you see that we don't see exactly what is being called, right? There's something missing there. We have a call to the creation of our cipher with CFB mode, and then we have call RAX. So here, it looks like for once, we don't know exactly what is being called. We're going to have to use the debugger. So I'm just going to copy the address there and see exactly what's in RAX when we reach this point. So let's move on there. Okay, and then you see when I read this point, we call crypto.cipher.xor keystring. So I suppose this is going to be this, the actual computation of the actual encryption taking place. Okay, and then encode to string, etc. So one thing that is missing there is going to be the AES key, right? I don't see any initialization vector either, but actually if you look for you and they can put it at the beginning of the encoded data, so the developer actually doesn't have to think about this too much. Go is, in that sense, a language that really does everything it can to prevent you from shooting yourself in the foot. So we have this main.encrypt function. We did not see anything that looked like key material in there. So what we are going to do is we're going to look around this function call and see what could be the key, the AES key being used. If we look around, well, the only thing that we can see there is this, right? We have this, what seems to be a global variable. Let's go there. One of the values is 20, which to me looks a bit like a size, and the other is, it looks like some offset. So let us try again. Let us look through the debugger exactly what is in there. So let me just put a breakpoint here. And I am going to relaunch the whole program. Okay. And put a breakpoint here. Looks like my layout got kind of messed up. Okay. It looks like my breakpoints do not work anymore. Okay, I don't know exactly what happened there. It doesn't matter too much, right? Oh, or maybe the reason why my breakpoint wasn't hit is because, in fact, now the file has been created. Yeah, you see on my desktop, I do have this config.dat.tmp because my previous debugging session, and so now I entered the other branch, and this is why I could not reach this again. So I'm just going to delete this and try again. Okay, so I get to the open file, get MD5 hash, those were my previous breakpoints, string, etc. Okay, and there we are. So let's follow this in the dump. Okay, this looks like an address. Okay, and you see now I have somewhere I have ended up in a region that contains random bytes. I think those may be my key bytes. I'm not 100% sure. Let's like this. Oh, maybe it's this actually. Following dump. Yeah, that really looks like some random data that could be used. So this could be used as a key. So to double check this, what I would have to do then is store this somewhere and try to see whatever data comes out of this main encrypt function, put that back into CyberChef and try to decrypt everything with this key and the IV that will be at the beginning of the output data. Please believe me when I tell you it's going to work. I'm not going to do this here because it's going to require me to like take the 16 first bytes manually and then put them back as an IV in CyberChef. It's just annoying, but it does work. So just doing this, we were able to get the AES key that is being used in the program, and we were also able to well, figure out what was going on there. So just go back here. One thing I want to point out at this juncture is really that in terms of reverse engineering, we haven't been doing much, right? We just skip over every assembly instruction and look at the function calls and use our debugger to just dump or sort of dump all the arguments that are being used. And then from there, we sort of guess / figure out what is going on in the program. So I do sometimes teach university classes with reverse engineering, and I'm pretty sure that the first year students who are very uncomfortable with assembly would actually be pretty okay with reverse engineering Go. So this is one of the main takeaways I wanted to share with you. It's the fact that if you try to follow all the instructions in the Go program, then you're going to have probably a very bad day. But if you take the quick and easy approach of looking at the various function calls, then we don't have to do that much work to figure out that AES is taking place. We can figure out where the key is. We can see that files are being created. We can just use the debugger to see which files and so on. And it's really some sort of easy win where we just get our answers without having to work too much for them. So I think this is really pretty cool. Anyway, let me go back to this main encrypt function. I think I wasn't there here, so I'm going to just do debug and then execute till return. Okay, so I'm just getting out of my main.encrypt. I'm going to move on and go up to this main write file there. So at the moment, if I go to my desktop, here, I'm supposedly, yeah, I do have this config.dat.tmp file here somewhere at the end. And if I press F8 here and skip over, then going back to my desktop, you see that, sorry, wrong desktop. You can see that now my file contains data. Now it's now 1 kilobyte big. And if I open it with my hex editor, yeah, you see it is a mixture of, it looks like base 64, but you know, with underscores and dashes. So this is the URL encoding, basically. Anyway, so at this point, what I would do here is I would try to make sure that I didn't make any mistakes. I would decode everything with CyberChef and verify that I do get back this string that we had initially, which was this one. And okay, so here, trust me, but it's going to be the case. And, well, it looks like we're done, right? This branch is over. So let us go back up a little bit and look at what happens if the file already exists. Right? So I'm just going to go back, all the way back up here. And if you recall, this was the beginning of this function where we started out by checking if this config.dat.tmp file existed. If it didn't, well, now we know what happens. We go into this branch and we just create it with some random, some hard-coded values. Otherwise, we go in there. And what we do here is all the way down there, because it's going to be useful. We figure out where the AES keys were, and so we should probably rename them. So let's do that. We went here in main.encrypt, and this here was the key size. So let me rename that AES. Okay, like this, and might as well do it because I'm pretty sure that on the other branch we are going to have references to those keys. Okay, so here we are back in the other branch, and so if the file does exist, then as you might expect, the keys get referred to or get loaded somewhere, and then we have this main.decrypt function, which I assume would be applied to this contents value that we got from the read file initially. And then like here, you have this gen split function, which works on the character pipe sign like this. So we just split whatever string was returned after we decrypt the configuration, and we split it with the pipe sign token. So it makes sense because this is sort of structure that we've seen. And so like, really nothing expected there. And then the strings are split. What happens then? We just move on. strcount A to I. So based on the tokens, we convert them back from strings to integers. And then, in fact, they will be stored back into the global variables that we've seen before. So this function, really here, of course, I'm just skipping over a lot. we've seen this already, but what would happen in this branch is the opposite of the other one, by which I mean that instead of taking hard-coded values and storing them in the configuration, then we would take the configuration, decrypt the configuration, and read the values back into the memory of the program and into the global variables. So we now sort of know what is taking place into this big, scrolling all the way up, define internal settings function. It's actually the function that processes the configuration of the program, and either the configuration does not exist and we create it, or the configuration exists and so we load it and put the values in the global variables. Okay, so I'm just going to go back here. And then we would be back there. So I think this is probably a good time to put a stop to this analysis. Of course, there is a lot going on in this program. What we saw there is just the very beginning, which is the loading of the configuration. It took us something like 2 hours to get there, but of course we really took our time. We really wanted to make sure that we had everything correct, and we wanted to check every argument under the debugger, etc. And also we constructed part of the program, so it was sort of a time-consuming effort. But overall, what happens next is we enter the main loop of the program, and now that we have the configuration, the program starts doing stuff on the victim machine. And so this is where he would connect to the C2 server and start interacting with the C2. And exactly the same way that we were able to look at how the configuration is loaded here in Go, we would be able as well to look at the protocol that is used to talk with the C2 server, look at the different keywords that can be sent by the C2 to trigger different actions on the system, etc. And just by doing this exact same process, but repeating it on the rest of the program, we would be able to understand all of it. And overall, I think with something like 2 to 3 days of work, then you can be sort of, I would say, confident that you would be able to see everything in this Go program, even though it is 5 megabytes big, and even though you might not have written a single line of Go code in your whole life. So I think we can probably stop it somewhere around here. If you do have questions, feel free to ask them. If there is something you want me to show again, it's the time. We do have a bit of, we do have some time left if you want to. And otherwise, yeah, thank you so much for listening to this tutorial. I really hope it was helpful to you. And that next time you do receive a malware written in Go, then it won't seem as daunting as maybe it was in the past. And yeah, so that's it. I will be there at least till the end of the conference. And I'm actually staying in Montreal for a while, so if you just want to go have drinks, feel free. Thank you so much, and I suppose that's it. Right, if you want the slides, I'm going to upload them on the internet. It will be the easiest way for everyone. Just save this on my desktop or something. Okay, so the slides should be in the same folder as the one where I put the samples initially. So p.kwi.ski or proxy.kwiatkowski.fr, which is the long form name for this domain. So the PDF is there. It's just the slides that I showed at the beginning of the presentation. Not much going on there, but at least you will have all the links that you might need. If you have any interest in the way that type information can be extracted from the binaries, this script that I showed you as well, I wrote a blog post on Kaspersky's website. It's called Extracting Type Information from the Binaries. So you do have the code on GitHub, but if you want to know exactly how this information is being stored in the binaries, you can find that there as well. Although it's kind of technical, this is all very technical details that don't really, unless you really need to retrieve this information by hand, if you have a script that does it, who cares where it is, right? Anyway, that's it. Slides are online. Again, if you have other questions, feel free to ask. Sorry? Same URL as the, let me, here you should have the URL on the screen.
I really want to read it because I was helping clean up the back yesterday until 3 a.m. and then I opened the doors at 7:15.
Yeah, so, no problem.
Just a bit all over the place.
Preventing debugging?
Yes.
Not really.
What is the standard
Well, for starters, I don't really see that much malware that uses anti-debugging. But usually they try to not use those techniques because it makes them stand out somewhat. So they try not to do this. Otherwise, Go will make this hard actually, because everything in Go comes from the library, and you have to work with you don't get to execute native stuff in Go. So you cannot really start working with the window structures. You cannot go into the PEB and that kind of stuff.
Is there no such alternative unless where you can just go window core no STD and then import the functions that you want from scratch?
I don't think so.